And Călugăreanu's work is exactly starting from Gauss linking number, fixing one of the two curves, and then constructing the other, i.e. the second curve, this one C2, as given by the C1 plus an epsilon away along some normal direction. And the normal direction then got Călugăreanu in some trouble, because you may think of this n as n principal normal cos theta. I'm not terribly sure about the correctness. I mean the plus or the minus somewhere here, but I just like to convey the idea that okay, something like this. We look at one of these curves as a dot here, as a cross-sectional plane. So this is, say, C1, and some along a unit normal, we have a second curve, C2 at a distance of an epsilon. Okay. So for an epsilon ribbon, we have the linking number well defined, and then you do the limiting case, lim as epsilon goes to 0 of the classical Gauss linking number between C1 and C2, and if you like, let me write x1. And the x2 is the x1 plus epsilon, let's say, n. And so is where this epsilon get into the formula, and when you take the limit, then you go to writhe and twist. Now, the trouble is that if you use this decomposition for the unit normal, you have normal and binormal, of course, and the trouble for Călugăreanu was when he ran into the case of everything worked, everything, but then he realized that you may have inflection points where curvature is equal to 0, hence this quantity you don't know what to do. We with Keith, we tribute to Călugăreanu's entirely the whole work, just because he considered what a mathematician would do, a limiting case from both sides. And by continuity, you show that everything is. If I were picking this n hat, and would identify that n hat with his u, then you perform, is a arc length derivative, and you do the arc length derivatives of normal and binormal. You use Frenet-Serre formula, and you end up with this interesting decomposition of twist. Twist depends on the two curves. On the epsilon and the thickness of the ribbon, you would write a twist as 1 over 2 pi total torsion. Say I now think of this as everything function of s, because I identified the second curve as the first in terms of s arc length plus this epsilon n in ds plus a contribution of this total angle theta over 2 pi. This would be along the C1, and this depends, well, this is torsion, total torsion. So here again we are back. Writhe plus total torsion are a function of the curve, one curve, C1, whatever. But then you have this contribution we called intrinsic twist and this total torsion. So the sum of the two gives you the twist, but this is the contribution you would have from a, consider a torus with a ribbon inside that has some twist. So you have 0 writhe, 0 total torsion, because it would be a planar curve for the torus, and you are left with this intrinsic twist.
So in a sense, what effectively this approach is doing, what Călugăreanu is doing, is saying that I naturally have a framing at every point along the curve, so long as it's regular, so I can define the Frenet framing everywhere. And so the integrated torsion is the twist of that Frenet framing, and then this is what you call
some intrinsic.
This intrinsic is then the integral of what the framing I'm interested in against the Frenet framing. So the Frenet framing gives this natural basis that this natural framing for the curve, but of course it has these problems with inflection points, which of course are extremely important for the dynamics, which is I guess what you're going to
So you see, you have a ride, you have this average ride from Fuller, and but you may have ride equal 1, for instance, even if the number of coils are 3 maybe, or 5, just because you just think of one orientation and the opposite, compensating each other. So in other words, if you look for quite elaborate, we looked into quite elaborate kinematics, so there's no physics, it's just playing with mathematics, to produce a curve that is having a lot of coiling in that sense, but not a big deal of twist or writhe, i.e. keeping fixed, say, one writhe. But with these opposite signs in pairs of coiling, you can show that you can, by this system of equation, it is very general here, you know, as you increase the number of parameters, you can do whatever you want. So you just think of these letters, A, B, C, etc. as 1, and functions of times as a linear function, a t, okay? And then you have an m and n, and then you can create just one twist, or one ride, if you like. You can create all sorts of kinematics. So that means that with one twist, you can create rather complicated geometries. So, in other words, we can say that with just a little bit of torsional energy, we can create a lot of complicated geometries. We don't need, for a highly coiled system, a very high number of twists, because of this compensation between plus and minus in the coiling. So I just show you very quickly that you know, this is the kind of curves we explored, and then you may have also multiple coils. Tell you one more thing about this twist. I'm backing from Mark's comment in saying that of course we may have twist equals 0, even in a highly twisted configuration, let's say, because we just need to compensate the amount. Sorry, this is not arc length, so it's a bit more complicated, but it's torsion basically, it's total torsion plus. So we may compensate the torsion effects along the curve with intrinsic twist that has opposite contribution. So the problem with the Frenet frame, that's why I mentioned in my talk Mercier frame, is that it's not orthogonal. In other words, if you follow the frame along a helical path, after one full turn, the frame is twisted by the amount of torsion that it gets from the helix. And in order to get it the right position, you have to remove that surplus of torsion that accumulates along the curve by subtracting a kind of intrinsic twist to the frame. So Mercier got it right in having an orthogonal curvilinear Frenet frame, and that is also something important. Now here we just, I think is a diagram that goes back to the work with Keith. We just pointed out that there is a singularity at the inflection point, but this singularity balanced with the other singularity here and there, so that the two singularities magically disappear when you compute twist, and that is reflected. So twist just is a continuous function, and that is reflected in the fact that the torsional energy that involves twist behaves perfectly smoothly when you go through inflectional states.